Thank you very much, Peter, for the introduction. Can you hear me?
Yes.
Good. And thanks to the organizer for inviting me to this lovely workshop. And I think it's going to be a very interesting week. Okay, so let's get started. So someone gives you a manifold with a Riemannian metric on it and a function. What can you do? There are several things you can do. You can write down, let's see if I can get this. No? Oh. You can write down Newton's equation like this. Or you can also write down a gradient flow. So my background is in Hamiltonian dynamics, so that's the first type of equation, let's say. So in that way, I'm a conservative person. So in other ways, I'm not at all, actually. But today I'm going to talk about the second type of equation, so the gradient flows, and how they come up in various aspects in shape analysis. Okay, so the formal setting is this. We have a Lie group, which is acting on some manifold Q. For now, I make no assumptions on this action. But let me just say that in this talk, I will assume that everything is nice and everything is smooth and so on. There's no analysis. And then you have a template element, Q naught, in this manifold Q, template or source. And you also have a target, Q1. And on G, on this Lie group, we have a Riemannian metric. And we assume that this Riemannian metric is symmetric under the isotropy subgroup of this Q naught. Right, so it fulfills this condition here for every, maybe Q is a strange notation here, but for every G in this subgroup anyway. Okay, and then we consider energy functionals. These are the functionals we want to use in our gradient flows of this particular form. So it's a lifted function. So you first define a function on your manifold Q, and then you have an action on Q naught. So that gives you a function. You pull it back, and you get a function on your Lie group. And we want to consider gradient flows with respect to this function. Also, formally, the equation we're interested in is this one. So this is the gradient with respect to this Lie group Riemannian metric. Okay, so let's continue. So let's take the special case when the Riemannian metric is fully right invariant. So that means that it automatically fulfills the symmetry property regardless of your action or your source point. So that means also that the right invariant metric, as you all know, is defined by just an inner product on one of the tangent spaces, and for example the Lie algebra of the group. So throughout this talk, by curly A, I denote the inertia tensor corresponding to this right invariant metric. And then some of you might know that there is something called the momentum map. So once you have this action, you can define a momentum map. Normally this momentum map comes up in Hamiltonian dynamics. Here it's interesting, it comes up also for gradient flows. So it's defined in this way. It's a mapping J from the cotangent bundle of Q into G star. So that's the dual of the Lie algebra. And it's defined like this for all Xi, algebra element Xi. And now, once we have this, we can work out what the gradient flow is. It's quite straightforward. It looks like this. So what is this here? G is our element in the Lie group. So this is the flow equation. And it's updated by this vector here, U, that depends on G acting on Q naught. And U is defined by this condition here. So you see how the momentum map comes in. The metric comes in here, gives you a vector field, and then you just advance the solution like that. So that's how the gradient flows look like in this framework. Yeah, so as I said, as you can see, this thing here now is the the gradient then with respect to this metric. And to understand this better, maybe we need some geometric intuition for what's going on here. So what is going on? Well, we have this manifold which has a group structure. It's our Lie group. Somewhere on this manifold we have the identity element. And then this manifold acts on Q naught, that's the element here down here, on the manifold Q. So by this action you get an orbit, the Q naught orbit, right? And we want to sort of flow along this orbit here to minimize the function, or to sort of minimize the distance to the target element Q1. That's the geometric interpretation of what's going on. And in fact, that's a point here as well, that because of this symmetry properties of your metric, the gradient flow up here actually descends to a gradient flow on the orbit. So you can think of this in two ways, either as a gradient flow on the Lie group or as a gradient flow on the orbit of Q naught. So the metric up here induces a metric on the orbit. Sometimes this metric corresponds to a metric on the full space here. Sometimes the action is transitive, so actually there's just one orbit, the whole space. We will see examples of both. Okay. So yeah, that's the next slide. If you can of course write down this induced gradient flow on the orbit, and then it looks like this. So it's the same vector field here, but now it's acting, it's the infinitesimal action on the Q element instead. And here, by the way, is how our functional comes into play, the F. Okay. So far I haven't said anything about how we choose this F, or how we choose our functional. So let's just say something about that. So of course the F will depend on the target point here, Q1. So I always denote it like this. But normally we want to divide our Q, our manifold where the group acts on, into two parts. One part, which is the actual shape space that we're interested in. But typically, at least in the case when you're working with infinite dimensional groups, you don't get a nice flow if you only consider this. You need some sort of regularization as well. So therefore, we also take another part, which I call R, which is also a manifold. And then we take our Q to be just the product manifold, right? So remember now, our group G is acting on both S and R. And then we take Q naught to be S naught, that's our template shape. And then some sort of regularization template, which I call R naught, right? And then Q1 is a different S1, that's the other shape, but it's the same R0. So maybe you see what will happen here. And then a typical form of the functional is something like this, where the first term measures the distance between S and S1, and the other term measures the distance between R and R naught. So somehow this means that we want to minimize this, but we also want to minimize this, so we don't want to go too far away from R naught. So that's why I think of this as regularization. And the parameter epsilon here, if you look at this map here, you can think of epsilon as essentially the slope of this orbit here, or the pink line. So if epsilon is large, then the slope is higher. So you tend to want to stay closer to R0 or S0, if you like. Okay, so that's the interpretation of these things, and how regularization comes into play. And once you have these things, so far I haven't shown you any concrete example, right? It's just abstract mumbo jumbo, if you like. But once you have this, you can sort of define things before you even start concretizing your flow. So for example, a very natural way to discretize time here is to consider the so-called Lie-Euler method. So remember, this is the gradient form of the gradient flow, right? So now the target element here is called Q star, because I want to use the index for time stepping. And then a natural method is just to use the Riemannian exponential like this for this, a natural way to discretize this flow. And this not only gives you an idea of how you can discretize your equations in time. Of course, in space you also need to do it if you're in infinite dimensions. But I think it also guides the design of your software, because you see exactly which elements you need in order to do this. You need an inertia operator, you need a momentum map, you need an infinitesimal action, and so on. So it's a nice way to sort of structure your software, I think. Okay, so that was the abstract part. Let's now get into some examples. Here are a few that I came across. And let me just say that this whole thing with the gradient flow, it started some years back. I was visiting Daryl Holm and Martins Preveris, and we were discussing various things and flows on coadjoint orbits. And then all of a sudden Daryl said, do you know about the Brocket flow? Should be two double T here, sorry. Do you know about the Brocket flow? I said, no, I have no idea about the Brocket flow. But then he showed me it's a very nice flow that is sort of closely related to the Toda flow, but it's a flow that diagonalizes matrices and also sorts lists. So it's a very interesting flow. We will get into that. And in this framework, you can describe the Brocket flow, and by doing that, you actually get a slightly new interpretation and a connection to entropy as well. So let me tell you about that later. There are also other examples. I will not get into all of them. I will mention something about these ones, and probably the most detailed part will be about this silly QR flow, because there you really see all the structures coming into play. So let's start with that. So in linear algebra you have various decompositions, as you all know, the LU factorization, you have SVD and so on. And now I'm interested in the QR decomposition. So it tells you that you take a matrix and you can decompose it, a square matrix, let's say, into one part Q, that is an orthogonal matrix, and one part R that is upper triangular. And there's an error here. It shouldn't be positive symmetric definite matrix. It should be upper triangular matrix with positive entries on the diagonal. Sorry, yeah, that can happen. So the point here is that there is a way to define a metric on GLN, space of matrices that are invertible, such that it is right invariant and the horizontal distribution becomes integrable, in the sense that the horizontal distribution at the identity are just the upper triangular matrices, and upper triangular matrices forms an integrable distribution. So you can actually integrate these horizontal vector spaces, and you get this cone here, which I denote by K. L is just the operator that A. Oh, it's just the horizontal distribution at the base point A. So A is an element in GLN. That's all. And you see what you do, you take the vector and you translate it back to the identity, and then you say that all the lower triangular, strictly lower triangular elements should be 0. That's what you do. Okay, so I will tell you the details, but let me just say now the outcome of this. So there is a way to define a metric up here, such that no, sorry, actually it is correct. It should be positive definite symmetric matrices here. Yes, you're right. So we have down here the space of positive definite symmetric matrices. We have an action of GLN on positive definite symmetric matrices by conjugation. And then we choose some element to act on, for example, the identity. That's what, to get the QR factorization. And then how do you get the QR factorization? Well, you start with some matrix A, like this. And then you start your flow at the identity. You project your A to get a symmetric matrix here. And then you follow the corresponding gradient flow in the framework I just told you that will evolve along this cone here. So it will flow along this sort of submanifold of upper triangular matrices, and it will give you an R. And when you come to the end of this flow, you know that you are on the same fiber as A, and being on the same fiber by definition means that A and R are related by just volume orthogonal matrix. That gives you the QR factorization. Okay, let me tell you some details how this looks like, because actually the metric you get downstairs corresponding to this nice metric upstairs is the Fisher-Rao metric. And how does the Fisher-Rao metric enter into this? Well, remember I said we have the symmetric positive definite matrices downstairs, right? That's our manifold Q. And if you think of these matrices, these symmetric matrices, as defining multivariate Gaussians, then you know that on the space of multivariate variate Gaussian distributions, there is a canonical metric, the Fisher-Rao metric. So of course, that induces a metric on this submanifold of Gaussian distributions, and that's exactly the one you get. So that's very nice. So actually, you can think of this as a flow on the space of Gaussian distributions. Okay. And what is then the Fisher-Rao metric? How does it look like on this submanifold? Well, so we have a symmetric positive definite matrix. Its tangent space is just the all symmetric matrices. It's given like this at each point. So it's an open subset actually of a vector space. So that makes things a bit easier. And then the Fisher-Rao metric is the one that looks like this. So it depends on the base point W, takes two vectors, symmetric matrices, and then this is what you need to do. And this metric, as I said, has this very nice property that it's invariant under the action of GLN on Pn, on the symmetric positive definite matrices. So that's straightforward to see. I'm not going to do it, but it means it fulfills this condition here. So in addition to this metric upstairs being right invariant, it has additional symmetry qualities. That means that after we descend to the metric, it still has a lot of invariance. Somehow this means it has invariance from both the left and the right. This is something very special that happens for this Fisher-Rao metric. Normally this doesn't happen. So this particular example has a lot of structure. And in fact, the other example I'm going to talk about later, infinite dimensional one, has a sort of similar structure. It captures all of this structure, but in an infinite dimensional setting. Okay, and now the metric I was talking about, the one on the Lie group, is compatible with this Fisher-Rao one. So actually, it descends to Fisher-Rao, and in this case, the action is transitive. You can reach all the possible positive definite symmetric matrices. So everything is very nice, and geodesics are essentially explicit because you know what the Fisher-Rao geodesics are. Okay, so now I said a lot about this metric, but I haven't specified yet what the function is, right? What the energy is. So let me do that now. So let's see, we have Fisher-Rao in connection to information geometry. What can we do? Well, we take entropy, obviously, right? So let's take entropy, or actually relative entropy. So this is the entropy relative to our W1. That's our target in the original abstract setting. And relative entropy is something that is very easy to define on the level of all probability distribution, and then on the submanifold of Gaussians it looks like this. Just a straightforward calculation to see what it becomes. Notice also that in this setting I have no regularization. So this R part that I introduced before, it doesn't exist, or it's zero. And finally, if we now look at the flow upstairs, so on the cone of upper triangular matrices, it will look like this. And Z is some skew symmetric matrix. I have an explicit expression for this, but there wasn't enough space to write it down, so I just write it like this. Think of it as essentially a Lagrangian multiplier. Okay, that's very nice. So that's our flow. That's our silly QR flow. Why is it silly? Because, well, no one would consider computing the QR factorization like this, right? But still, I think it adds a lot of nice geometric features, and as I said, you can extend this to infinite dimensions, and then becomes more interesting. Something about analysis. What can you do? In this case, it's extremely nice. You can prove convergence very easily, and the central lemma is the following one: that actually the Fisher-Rao metric is a so-called Hessian metric. So there is a potential for this metric defined by some function, and that function is exactly the entropy. So that means that in fact the Hessian of our energy functional is exactly the metric tensor. And of course, this means that we can immediately say that the flow fulfills this condition here, where d is the Riemannian distance induced by the Fisher-Rao metric. So in fact, we have an explicit expression for d. So it will decrease exponentially with time, like this. And this we see also in numerics. If we try, this is a super simple example. I start, I know in this case what the r is, right? So, and from this I project down, I get the w. And then we start the flow at the identity, right? So you have two zeros, two ones and two zeros actually, but it's a symmetric matrix. This upper triangle, so we only need to consider this one. And then the flow goes like this. So, and if you look at the energy, it decreases exactly according to what we expect. Okay, so that's nice. That's the first example, which has a lot of structure. We'll come back to an infinite dimensional version of that. But before I do that, I want to say something about Brockett's flow as well. So in this case, the Lie group is smaller. It's just a set of orthogonal matrices. And you take the canonical metric here, the one that is given by minus the Killing form. And then the energy functional looks like this. So you take the energy functional of Q to be some sort of Frobenius inner product here, where M is, so what did I say about the Brockett flow? Well, it's a flow that somehow takes a matrix and makes it diagonal. And not only that, it also sorts its eigenvalues somehow. And so the flow we're going to consider is sort of, we want to decompose, make a spectral decomposition, let's say, of M, which is a positive definite matrix. So think of M as the matrix we want to find, we want to diagonalize. But in order to do that, we need to specify sort of the order of the eigenvalues, and that you do by specifying a matrix, a diagonal matrix N. So that's what Brockett just suggested, and it turns out that it has this nice form. And he considered this energy functional, and then of course he had this metric already, so he wrote down the gradient flow, and he gives you these equations here. And you can notice already that if Q transpose MQ is diagonal, then this thing is 0. So at least just by looking at this, you see that if you manage to diagonalize this by Q, then that's going to be a stationary point for this flow. Okay. But let's say something more. So what we get by taking this and trying to interpret it in this framework is a new interpretation. So of course, I have to point out here that the action in this case is not transitive. That's the whole point, right? You want to sort of flow, but you don't want to destroy the eigenvalues. They should remain. So it's a nice spectral flow. So spectral information is still retained. But the point is that you can do this and you define again relative entropy, and now it's relative to n, to this diagonal matrix, right? And it's a flow on a smaller space now because it's just on the orthogonal matrices. And then you work out everything in this framework we had, and it turns out that you get this form of the equations. And if you interpret W, you express this instead in your variable, in another variable sigma, you get this form of the equation. This is called the double bracket flow, and that's just another way to write down the bracket flow. This is sort of how you get from this framework into the bracket flow. Okay, it's a nice example because it connects the bracket flow to Fisher information. Yes, okay. So here now comes the infinite dimensional example. And this is some work we did some time ago with Martin Bauer and Sarang Joshi. We're still working with it, but this is the first part. So the setting is the following. We start with a compact Riemannian manifold M. G denotes there's a lot of G here, so you have to keep track of all of them. Right? This is the lowercase g is the metric. And then our group now is infinite dimensional. It's a space of diffeomorphism of M. As S, the shape space, we take the space of probability densities. So it's densities that are positive, and they integrate with respect to the Riemannian volume form that I call mu to 1, like this. You can also think of this as top forms. It's just a matter of what you prefer. In this case, we sometimes need regularization as well, and in this case we used a very simple type of regularization. You just penalize change of volume. So in this case, R, the regularization space, is also the space of probability densities. So the manifold that we're acting on is a product between dens with itself. And the action is by push forward. It's not composition. So I will come back to that later. That means that we're not just taking our density function and composing it with phi inverse. It's you have to multiply with the Jacobian determinant as well. In some cases this is a good action, in other cases it's not. I'll say something about that. You induce a right invariant metric. It turns out that in this case the metric looks a bit like this. So this is and this Laplacian here is de Rham Laplacian. You should think of this as one form, so then you take it de Rham Laplacian. And the reason that this is a good choice is because then you will get this nice connection to Fisher-Rao. So actually, this choice here and the dot dot dot, there's some extra terms you need to add to make this non-degenerate, and those terms depend on your manifold. You know, essentially it depends on the first cohomology of your manifold, but I don't want to get into details. So we have something like this, a nice metric, and it has a lot of structure. For the energy functional, we take the Fisher-Rao distance, that's df, between rho 1 and rho. This is the sort of matching term, similarity term, and then we take epsilon. So this is the regularity term, and again Fisher-Rao distance between just the unit density rho and sigma. Remember, we had to specify this for both rho and sigma being in Q in dens times dens. And I said there's a lot of structure because this metric is connected to this one. So this one actually descends. So the metric here descends to Fisher-Rao, which gives this distance. By the way, the Fisher-Rao distance is like a spherical version of the Hellinger distance. So maybe some of you know about the Hellinger distance in statistics. And so one ingredient to be able to do this was to compute the momentum map, right? So we do that. Actually, yeah, should be 2 copies of densities, but you just add another one, so it's okay. And then in this case it just looks like this, and the gradient flow on the orbits now have this form. That's just a straightforward calculation to see that. And here it's a little bit complicated, but everything is explicit because we can explicitly write down the Fisher-Rao distance. And here you see the regularization coming into play as well. Okay, so that's the flow, and what can it be used for? Well, one thing that we have been using this for is to actually draw samples. So what is the problem? Well, you're given some probability distribution and you want to generate n samples from it. So normally, in most cases I would say, the best choice is to use some sort of Monte Carlo based approach, right? But there are special cases where you could use other types of techniques, so the sort of transport type techniques. And that's when m is low dimensional, let's say dimension 2, 3, or maybe up to 4, but not so much higher. And your mu is very complicated, it's very non-uniform, and n is extremely large, let's say over 1 million, 10 million, something like that. In this case, it might be useful to use the transport map approach. And what you do there is you basically solve an optimal transport problem. And you use the transport map to sort of, you sample first from a uniform distribution, and then you use the transport map to transfer your samples into this non-uniform distribution. So, we can reformulate this problem into a new one, which is the following. We're given a density, we want to find a diffeomorphism that is minimizing some distance under the constraint that it takes a reference, let's say uniform distribution into mu. This is an optimal transport problem. If you take this distance to be just some L2 distance, you get, oh, it shouldn't be L2 Wasserstein, it's just the L2 distance upstairs here. Then you get normal optimal mass transport. And you can do that as an approach that people have been looking at to draw samples. One problem, of course, with the optimal mass transport, you have to solve the Monge-Ampere equation, which is a PD that is very, very nonlinear. So there are good methods for doing this, but our approach is somewhat different. We want to instead use this different metric structure. So we're not interested in L2 and Wasserstein. We want to use instead the Fischer-Rao point of view. So we've been doing this, and the good thing here is that essentially the gradient flow is just going to flow along Fischer-Rao geodesics. And we know explicitly what the Fischer-Rao geodesics are. We can always connect 2 points with the Fischer-Rao geodesic and then lift it. So here we get an almost explicit algorithm for this. In each time step we just have to solve a Poisson problem, which is much easier than solving a Monge-Ampere equation. So here is an example. Here is our sort of weird density distribution. We compute the warp. And then once we have computed the warp, we can draw our samples. And once this warp is computed, it's very fast to draw new samples. So 10 million samples, less than a second on my laptop here. So then you might think, okay, wow, that's very nice. So can we not use this rich geometric structure to actually solve registration problems? Well, you can, but you get crap. So one problem is, in order for this to work, you need to work with strictly positive densities. So the first thing you have to do is, if your density is somewhere 0, or your image, let's say, is somewhere 0, you have to add a little grayscale to it. So that already makes it a bit, maybe not so nice. And then if you actually compute the Fischer-Rao geodesic, you see that it's basically just blending between the two images. And the transport map you get is not good at all. It's not what you want for registration. Okay. But there is a little but here. I didn't use regularization yet. So if you look carefully here, you see the problem is that we're expanding things when we don't want to expand things. So essentially, remember now, we're not using just the composition as an action. We're using the density action. So what is happening here is that instead of taking the white pixels and moving them to somewhere else, you just take white pixels and expand them so they become grayish. Or you take the gray ones and you compress them so they become white. That's sort of what is happening here, and that's why it's not so good for registration. But if we add a penalty term that penalizes change of volume, then this might work. And yeah, then it works much better. Of course, in this case, we don't have this semi-explicit form of the geodesic. We actually need to follow the gradient flow. But that's still quite fast, although not as fast. And then you get a much nicer result. So here is the mapping from the J to the V. And you see now you don't exactly reach it because we have this penalty term that is stopping it from going all the way, let's say. And in this case, the warp looks more like it should. So this is still a toy example, right? We did one little more advanced example. And this was CT imaging of a breathing lung, and this was some data from a rat, where someone did CT imaging of a breathing rat. Sarang got the data, I have no idea from where. But anyway, the observation is that here you see that when the lung volume changes, you can see in the images that the density is changing. So that indicates that actually here the composition action is not the right one. I'm not saying that the density action is the right one either, but something along that line. We're now thinking about something called alpha densities, which are like half densities as well. But anyway, you need something that is more similar to a density action. So we've done this in a 3D example, and here are some results. And in this case, we are penalizing, or the regularization is a bit different, because we want actually, what do we want in the lung? In regions of the lung where you have low density, we want a lot of compression and expansion. So we don't want to penalize change of volume so much there. But where you have tissue, higher density, there you essentially don't want to change the volume at all. So there you want to penalize things. So we did that and then considered the flow. And here you see the resulting Jacobian. And the nice thing here is that you see the parts that have tissue, those are the white parts. They essentially don't change the volume, or very little. And then the parts here, there is air, the lung, that is compressed or expanded. If you do the same thing with LDDMM and just a function decomposition, you get these strange compressions and expansions, which is maybe a bit non-physical. Okay, so this was the first preliminary study as well, but it shows that the method has some promise. So, okay, I'm talking about shape analysis at this conference with lots of experts on LDDMM. So how does that fit into this thing here? Well, it fits. Let me show you how. So again, we're on a Riemannian manifold. We take the group of diffeomorphisms. And now our shape space is the space of functions, let's say images. And the funny thing here is that the regularization space is the full group. It's again diff M. The action is by composition from the right. You take some it doesn't have to be a right invariant H1 metric, right? I mean, it can be any metric, the right invariant metric determined by a kernel. That's normally how you do it. For example, an H1 metric. And then the energy function looks like this. So you have two parts. The part where you match the images, like this, and then the regularization part, and this measures the distance to the identity with respect to this right invariant metric on the group, right? So why is this LDDMM computationally expensive? Remember, to compute this gradient flow, we need to take the derivative of this map with respect to both I and eta, right? And computing the derivative of this is complicated because we don't have a closed form expression for it. So we need to solve the differential equation, the EPDIF equation essentially. So of course this is not the best way to solve LDDMM, but it anyway tells you a little bit about the complications here. We can write this down, but it's a little bit complicated or it's expensive, let's say, to evaluate it. Yeah, as I said. But anyway, it fits the framework. So if you see it from this point of view, it's obvious that you can do some sort of regularization which will make the method cheaper. I think these ideas are not new. Joshi, Pennek, and probably others in the audience have considered similar methods. So what we're doing is, instead of taking here the space of diffeomorphisms, we take the space of Riemannian metrics. So now I'm connecting some of this stuff to Peter's talk this morning. So we take here the space of Riemannian metric, and we let G, or our diffeomorphism, act on the reference metric that we have on our manifold. We take a right invariant metric defined by a kernel. The action is by composition here and by push forward here. And then the energy function is something like this. And now this thing here is the what did you call it? The Ebbing metric, or the metric, the L2 metric on the space of Riemannian metrics, right? So the energy functional F looks like this. So if you actually write down what E is, maybe that's more intuitive here. It's like this. You get this matching term here, it's the normal one, and then just this thing here, and the second term here, the action of the diffeo on the metric. That's in mechanics, that's called the deformation tensor. So somehow this measures how much you deform your metric, right? And you don't want to do that too much. And because of this nice geometry of the space of Riemannian metrics, we have an explicit formula for this thing here. So this will be cheaper to compute the derivative of this. And if you do it, you get the gradient flow that looks a bit like this. The first thing you have to do is to compute the momentum map. Straightforward. So alpha is now let's say a tangent. Is in the tangent space of metric tensors. Actually, it's in the cotangent space. This is supposed to be a momentum map. So this is a generalized divergence, let's say. And then the gradient flow looks like this. So A is the inertia tensor, and I is the metric. I is the image, and H is this deformed metric that we don't want to deform it too much. So by the way, now I'm always writing down the gradient flows on the orbit. You can of course always also write it upstairs directly in terms of the diffeomorphism. Essentially, it just means you take your vector field and you integrate it to get the diffeomorphism. Okay, so that was LDDMM, a little bit about that. The last example, a work in progress. This is with Ozan Öktem, who's here today. The setting is similar, very similar to what we had before. We start with the Riemannian manifold. We take our group of diffeomorphisms. We take some shape space, typically images or densities. That's what we've been thinking so far. And maybe here it will be densities, I think. And then you take your regularization space as either regularizing just change of volume, penalizing change of volume, or the whole deformation tensor. But now the difference is that we want to use this framework to solve inverse problems in tomography, for example. So we have a forward model that takes our shape into some data space, H. Think of this, for example, as a ray transform. That's the simplest example, I guess. Or that's one example. And then our energy functional looks like this. So this is our forward model. We want to match the data, but we don't want to. We want to do this by deforming a template. So sort of this means you put the information into your model. You say that, okay, we know that what we're looking for is a deformation of a template, and it's deformed by this group of diffeomorphisms. And then, of course, we need some regularization here as well. Right? So you can do this, work out the flow. It gives you something. The flow looks something like this. So notice here that you get T star here from the forward map, and here you get some matching between the data. And then you have this regularization term as before. This gives you a flow of the density row. So in this case, we did density matching and the metric, the deformed metric. And here are some preliminary results for this. So we start, this is a 2D example. We start with a template like this. In this case, the forward model is just a ray transform. So we take only 3 ray transforms, okay, 2 minutes, but 3 ray transforms from 3 different angles. That gives you the blue data here. So this is the ground truth. This is the template we use. And then on this blue data, we add a lot of noise. That gives you the green data. That's the one we actually use in the reconstruction. And we let this flow just continue, and this is the result. It's not a perfect C, but it's pretty good given we just have 3 projections. Okay, that's all I had to say. Thank you.
So, many thanks. Other questions? Please.
You mentioned for the QR flow you had a convergence result.
Yes.
What about convergence results for densities or LDDMM? Or do you have even existence of the limit point in those?
So in the simplest case, where we had no regularization, yes. It's obvious. You don't need anything, since we know that we can always connect two densities by an explicitly. So using that, and using the fact that it's convex in this setting, I think we immediately get existence result for very small regularizations, for small regularization parameter. When it's large, then of course you have to look at the convexity of this other functional, and that we haven't done yet. But that's of course something that we need to do. Yeah.
So this Ibn metric is not geodesically complete, so you cannot reach very far with the geodesics. Do you feel this in the numerics?
No, because remember, we're only looking at one orbit, and it's the action of the diffeomorphism, right?
Yeah.
So the volume never changes. So in fact, I think we can think of this as the space of metrics with constant volume, and on that space everything is fine, right? So I don't think we will ever run into that problem.
Other questions? If not, thank you very much once.